Welcome back. In the last session, we had a discussion regarding Bayes' theorem and how to apply Bayes' theorem to solve machine learning problems. In today's session, let us try to understand the relationship between Bayes' theorem and the problem of concept learning. So what we mean by concept learning? In concept learning, we are given the examples, those are labeled as members or non-members of the concept. And concept learning enables us to automatically infer the general definition of some concept. Or in other words, concept learning is inferring a Boolean valued function from training examples. Bayes' theorem can be used for building algorithm for concept learning. Since Bayes' theorem provides a way to calculate the posterior probability of each hypothesis given the training data, we can use it as the basis for a straightforward learning algorithm that calculates the probability for each possible hypothesis and then outputs the most probable one. In line with the discussion that we had in the last session, we are going to formally come up with a brute force map learning algorithm. Assume the learner considers some finite hypothesis space capital H, which is defined over the instance space X. The task is to learn some target concept C, which is Boolean valued. The first step of the algorithm deals with computation of the posterior probability for each hypothesis H in the hypothesis space capital H. This posterior probability is computed using Bayes' theorem. So the expression for Bayes' theorem that we have studied already is written as probability of H given D is equal to probability of D given H into probability of H divided by probability of D. In the second step of the algorithm, we are going to output the hypothesis given as H map such that this hypothesis is having the highest posterior probability out of all hypothesis probabilities in hypothesis space H. So it is given as H map is equal to ARG max over all hypotheses in hypothesis space H of probability of H given D. Now if there is a large hypothesis space, meaning there are many number of hypotheses in the hypothesis space, this algorithm may require significant computations because it applies Bayes' theorem to each and every hypothesis in hypothesis space H and calculates probability of H given D. Due to huge computations required, this algorithm may prove impractical for large hypothesis spaces. But still, this algorithm is of interest because it provides a standard against which we may judge the performance of other algorithms. Bayesian analysis can sometimes be used to show that a particular learning algorithm outputs a maximum a posteriori hypothesis or map hypothesis, even though it may not explicitly use Bayes' rule or calculate probabilities in any form. We are going to consider one such problem of learning a continuous valued or real valued function. You will see that the final expression that gives us maximum likelihood hypothesis in this problem will not directly include any kind of probability estimating terms, but this expression is derived based upon analyzing the probabilities and Bayesian analysis. Assume a learner for real valued functions with instance space X and hypothesis space H. Consider any real valued target function f that takes instance space X and outputs a continuous value or a real value. We have a set of n training examples given as xi di, where di is a noisy target value. This di can be written as the expression di equal to f of xi plus ei. Please look at this. Di is equal to f of xi plus ei, where f of xi is the noise free value of the target function. And what is this ei? Ei is noise, or it is a random variable drawn independently for each xi according to some Gaussian distribution with mean equal to 0. The task of the learner is to output a maximum likelihood hypothesis, or equivalently a map hypothesis, assuming all hypotheses are equally probable a priori. Let us consider a simple example of such a problem, that is learning a linear function. Let us see this visual illustration. A linear target function f is depicted in this figure by a solid line, and a set of noisy training examples of this target function are shown by the dots. Dashed line corresponds to the hypothesis HML, that is the maximum likelihood hypothesis with least squared training error. Here we can observe that the maximum likely hypothesis is not identical to the correct hypothesis f. Why this is so? Because the maximum likelihood hypothesis is inferred from only a limited sample set of noisy training data. As the training data is limited, not necessarily the maximum likelihood hypothesis exactly maps to the correct hypothesis f. The maximum likelihood hypothesis HML is the one that minimizes the sum of squared errors, and hence this HML can be expressed as ARG mean H belong to the hypothesis space capital H over the summation of I from 1 to n di minus hxi whole square. So here, as usual, we are computing an error between the target value and the value computed by the hypothesis for every example in the training set. So we are having the sum of square error, and we are finding the hypothesis or maximum likely hypothesis as the hypothesis that is giving us the minimum error. Now, as I mentioned earlier, in this expression for HML, we are not having any term that computes or deals with probability. We are not going into the details of the derivation of this expression HML. But to derive this expression, we need to use two probability terms, the probability density function and the normal distribution. So, the essence is, as I said earlier, Bayesian analysis is used here for particular learning algorithm that outputs map hypothesis, but it is not explicitly using Bayes rule or not computing any kind of probability explicitly. This is how we related the maximum likelihood hypothesis and the least squared error hypothesis. But it is important to note the limitation of such kind of a problem setting. This analysis considers noise only in the target value of the training example. That is, di is defined as the addition of noise-free value of a target function and a random variable ei. But this problem setting does not consider noise in the attributes those describe the instances. For example, if the problem is to learn to predict the weight of a person based on the person's age and height, then the above analysis assumes noise in the measurement of the weight, but it assumes that age and height are measured perfectly without having any noise. The analysis may become significantly complicated if these simplifying assumptions are removed. So let us proceed further to look at one of the most interesting and important concept under Bayes learning, and that is Bayes optimal classifier. So far, we have considered the question, what is the most probable hypothesis given the training data? I'll repeat the question. So far, we asked what is the most probable hypothesis given the training data, and we tried to find out the most probable hypothesis so far. In fact, the question that is often of most significance is the closely related question. What is the most probable classification of the new instance given the training data? I'll repeat the the question once again. Please listen carefully. What is the most probable classification of the new instance given the training data? To find out most probable hypothesis, let us recall what we did. We used training data. We computed probability of each hypothesis in hypothesis space given training data D, and we found out the hypothesis having the maximum probability H given D, and we denoted this hypothesis as H map. So this is how we learned H map, and we said H map is the most probable hypothesis. But the question is whether H map is the most probable classification as well. To clarify the distinction between these two questions, let me illustrate this with one example. So, let us assume that we are having the hypothesis space containing three hypotheses H1, H2 and H3. Also, let us assume that the posterior probabilities given training data D are as follows. Probability of H1 given D is 0.4. Probability of H2 given D is 0.3, and probability of H3 given D is also 0.3. So, if we are having this data, obviously we may conclude that H1 is the map hypothesis. Why? Because H1 is the hypothesis that is giving us the maximum probability of H given D. Now, let new instance X is classified as positive by hypothesis H1 but negative by H2 and H3. As H1 is most probable hypothesis, this new instance X will be classified as positive. Here we classified new instance X based upon H map, that is the hypothesis which is most probable, and hence we classified X as having the class positive. But if we consider all hypotheses, the probability that X is classified as positive is 0.4, that is the probability of H1 given D, and the probability that it is negative is 0.6. How? Because two hypotheses are classifying it as negative. So, probability of H2 given D plus probability of H3 given D is 0.3 plus 0.3 is equal to 0.6. So, the probability that new instance is negative is 0.6, and hence the most probable classification would be negative, which is different from map hypothesis. I hope you must have understood the concept and the distinction between two questions. What is the most probable classification and what is the most probable hypothesis? So, to come up with the most probable classification of the new instance, we are slightly modifying our earlier expression. The most probable classification of the new instance is obtained by combining the predictions of all hypotheses weighted by their posterior probabilities. So the expression can be written as probability of Vj given D is equal to summation over all hypotheses in hypothesis space H, probability of Vj given Hi into probability of Hi given D. What is Vj here? Vj is the possible value of a label and that belongs to some set V. So, for every possible value Vj, we are computing the probability of Vj given D. The optimal classification of the new instance is the value Vj for which probability of Vj given D is maximum. So, Bayes' optimal classification is given as ARG max Vj that belongs to capital V, which is the set of all labels, over summation Hi that belongs to capital H, probability of Vj given Hi into probability of Hi given D. Please look at this expression. This expression gives us the Bayes optimal classifier. So, to interpret this expression, we are finding out this summation for every Vj or for every label for all the hypotheses in the hypothesis space, and for whichever label Vj, this summation comes out to be the maximum summation. We say that that Vj is the class for new sample that is presented to this classifier. To understand it better, let us go through one example. Let us assume that we are having set V that includes two labels, positive and negative. We are having three hypotheses in our hypothesis space, H1, H2 and H3. Various probabilities are being provided. So, probability of H1 given D is 0.4, probability of H2 given D is 0.3 and probability of H3 given D is 0.3. Next, probability negative given H1 is 0 and probability positive given H1 is 1. Probability negative given H2 is 1. So, probability positive given H2 is 0. Probability negative given H3 is 1 and hence probability positive given H3 is 0. Now, as there are two values in set V, these values are positive and negative, we are supposed to compute two quantities. First is for value positive and second is for value negative. So, for value of V equal to positive, we are having here the expression summation over Hi that belongs to capital H, probability of positive given Hi multiplied with probability Hi given D. So, this comes out to be 0.4, whereas for value negative we are having the expression summation over all hypotheses in H probability of negative given hi into probability of hi given d. So it comes out to be 0.6. So how we have computed these values? Just we have substituted the known probabilities for h1, h2 and h3 in respective expressions, and we computed these values 0.4 and 0.6. Therefore, by making use of Bayes optimal classifier, we can find out the most probable classification for this problem having three hypotheses h1, h2, h3 as negative. Any system that classifies new instances according to the equation of Bayes optimal classification is called Bayes optimal classifier or Bayes optimal learner. Why this is called as optimal classifier? No other classification method using the same hypothesis space and the same prior knowledge can outperform this method on average, and hence this classifier is known as optimal classifier. This method maximizes the probability that the new instance is classified correctly given the available data, hypothesis space and prior probabilities over the hypothesis. So I hope you must have understood the concept of Bayes optimal classifier. Although the Bayes optimal classifier provides best result, it can be expensive for large number of hypotheses. The expenses due to the fact that it computes the posterior probability for every hypothesis in H and then combines the predictions of each hypothesis to classify each new instance. Here comes an alternative, less optimal method that is known as Gibbs algorithm or Gibbs classifier. This algorithm has two steps. Step number 1, choose one hypothesis at random according to the posterior probability distribution over hypothesis space H, or according to posterior probability H given D. Step number 2 is use this H to predict the classification of next instance X. The surprising fact here is, assuming the target concepts are drawn at random from hypothesis space H according to priors on H, it is found that the misclassification error, expected misclassification error for Gibbs algorithm is less than or equal to twice the misclassification error for Bayes optimal classifier. That is, the expected misclassification error is no worse than twice the Bayes optimal classifier, and hence this classifier is also widely accepted and used. With this, we are going to conclude this session. In the next session, we'll be focusing upon a most popular classifier under Bayes learning, and that is known as Navy Bayes classifier. Thank you.